second. Okay, so I hope you can hear me properly while you're responding. I guess you can hear. So we're on lecture 9. Actually, this is the second time we're on lecture 9 because we didn't finish last time. So let's remind ourselves what we covered so far and where we are. We discussed the structure of ROS as a whole. We know that ROS consists of different repositories. In different repositories, there are different ROS stacks or separate packages, and there are many repositories. There is no single repository where the whole ROS is. There are many different repositories, and you as developer can add some repositories. If you publish your packages, they become within a specific procedure, they become available for different ROS users. And we discussed ROS file system. We know that ROS basically stays in two places on your PC. First one is installation directory, where standard packages are located and standard setup scripts are located. And second one is your user working directory. There can be many of them, but usually, especially in the beginning, we just have a single working directory where we place all packages we develop. And then we discussed that there is a certain structure of our working directory. There is src folder where we put all packages, and each package has to have two files. CMakeList, because it is used by Katkin, which is build system of ROS, and the second file is manifest file, which is called package.xml, which also has a specific structure and contains different information on our package: who is an author, who is a maintainer, which version of package is available at the moment, and many more. And we know that from this package.xml, there is data which is used to generate wiki page about a package, and also it is used in CMakeList to know which dependencies our package has. Last time we initialized our workspace and created the first package. We will do these steps today from the beginning. They will not take long, but we will try to go from the package creation to some node creation today. But we will first start with theoretical part. So what else we covered? Specific structure of a package. So usually there is src directory within our package where we locate source files, and there are many more possible directories within our package. For example, today we will create message directory to define our own message types. But there can be many more standard directories within the package directory. We then discussed how package.xml is structured. Today we will take a look at it again in a real package. And then we discussed Katkin, which is automation system for building software within ROS. Katkin is built upon CMake, which is standard build facility for C++. So it is widely used framework or automation build system for C++. And Katkin is just extension of CMake with some macros and Python scripts, which just make our life easier. In ROS, it works both for Python and for C++, which is really convenient. We have to use a single syntax within our CMake files to build any software we are writing in ROS. Then we discussed some particular commands within our CMakeList, and again, we will cover part of them today. Okay, and now let's discuss something new about communication types in ROS. We will start today and again finish in the next lecture, because there are several types of communication with, between nodes in ROS. And today we will see the simplest one, which is topic. When we were launching our Turtlebot simulation, we already have seen how topics works, how data is distributed within topics. So this is the most common and basic type of communication between nodes in ROS. But there are many more. As you can see, topic has a single arrow from one node to another, which means it's one-way communication from one node to another, or from one node to many, or from many to many. But still, it is just one-way communication. There is another type which is called surveys. So there are services in ROS. which consist of request and response. And as you can see, it is two ways communication. So one node sends some request to another and then gets a response. And there is a third type of communication, which is called actions. Actions are quite similar to services, but services, we will discuss in a minute, are blocking. So while we are waiting for response from the server or from another node, we cannot continue our job. So node 2, which sends request, waits until it gets response. And if response comes in a long time, this node is blocked. So this is a blocking type of communication. While actions are designed for longer communication of the type request response, and they're not blocking. So we are sending request and then periodically get feedback, continuing doing what we were doing, like within our code, some computations or some useful tasks. And then within some time, we get result. So this is quite similar to services, but non-blocking type of communication. And there is, we can consider fourth type of communication, which is parameters. We discussed parameter server. So this is just a convenient way to store parameters within Ros, to configure our nodes, configure our system. There is a specific parameter server to which we can put some parameters, from which we can read some parameters, and so on. So let's discuss in a bit more details these three types of communications. So first one is topics. There is usually publisher and subscriber in this communication. So publisher publishes some data. In this particular example, it is odometry, and there is a simultaneous localization and mapping algorithm which reads this odometry. But it is important that topics allow many-to-many communication. So it is not only one-to-one communication, it is end-to-end. So here's an example where we have a single publisher, but two subscribers. It is also possible with topics, and also many publishers are possible. So this is streaming type communication. So data is streamed continuously. This is something we have to have in mind when we're designing our system, that in topics, data is streamed continuously. And for example, if you have some huge pieces of data which do not change, it is not really convenient to use this type of communication. Imagine a static map. For example, we have a map server and we want to publish a map. But if we know that this map is static, it doesn't change, it doesn't make sense to publish it continuously, because it is a heavy operation which takes a lot of resources to publish this map. And in this case, we can use, for example, services. So this is as we already know, a request-response type of communication. And for such type of data as map, which doesn't change, it is practical just to request a map, get it back, and that's it. And maybe request it in a long period of time when we know that map could change. Another example here is just time, for example. Imagine we have a server which knows current time. So we can ask current time and get value back. We don't need to stream this data continuously. For example, we have an application where we just periodically check some timer. We don't have to stream timer value continuously. We can just ask sometimes and then get response back. But important here, and you need to remember that this is a blocking type of communication. So usually service is designed in a way that they're lightweight. So there shouldn't be heavy operations within server to get to respond to client. Because if you have some heavy operation here on the server, client gets blocked and cannot continue some useful operations. And that is why this is a bad practice to perform some heavy operations on the server side. The service has to be lightweight, so quick request, quick response. And if you have to design some heavy operations which performed on request, then you can use actions mechanism. So imagine we have a server which can do some housework for us, for example, washing dishes, some robot which can perform housework for us, washing dishes, doing laundries, and so on. And we just get the request to do the job. we periodically get feedback, and we are continuing to do our own things. So if the client, for example, some other node which performs, I don't know, localization, it can continue to perform localization while server performs some useful work and periodically gives feedback to us. And in the end of this work, it just reports that work is done. So this is actions mechanism. It is not quite actually popular in ROS. It exists. It is used many times, especially with industrial robots. For example, you ask robot to reach some particular pose, and it takes some time. And in this case, actions is a good mechanism, because you can get the request to reach some pose. Meanwhile, you can continue some useful calculations, some planning, or so on. And then once the goal is reached, you get the feedback that the goal is reached, and you can, for example, plan new trajectory or something like that. So it finds application in such cases. But actually, services and topics are much more widespread in ROS systems, because these are the basic two types of communications. But you have to be familiar with actions, because sometimes it is really useful to design your system using actions. So this is an image from a book you have in your references, which shows how communication in ROS works in case of topics. And you remember this example we launched last time. There was turtle sim node. There was teleoperation key node, which allowed us to control the turtle with a keyboard. And that is how this system worked, actually. In the first place, when we launch our simulation, it tells ROS core to be particular ROS master, which is some kind of DNS server, you remember. It tells it that there is a node called turtle sim. It publishes turtle 1 SIMD velocity. It subscribes to turtle 1 SIMD velocity topic, and it has particular address, because under the hood, ROS uses actually TCP UDP type of communication. So each node and each topic have their own addresses, and ROS master is responsible to remember these addresses and to give them to other node when they're asking. So ROS master keeps all this data to know what is launched and to know how to connect different parts of the system. So our turtle sim node tells this information to ROS master, that it is first of all launched, and it waits to subscribe to some particular topic. But there is nobody who is publishing data to this topic, but still ROS master knows that it awaits. Then we launched second node, which is turtle teleop key node. It tells the ROS core, first of all, that it is launched, it has particular address, and that it's going to publish some particular topic. And then ROS core tells the turtle sim node that now there is some node, some other node, which actually publishes this data. And to read them, this turtle sim node needs to access this address to read the data. And after this communication is established, ROS master is not doing anything anymore. These two nodes knowing addresses of each other, and communication happens just between them. Topics, data is streamed into topics, and they're communicated strictly through it, with each other without using ROS master. So ROS master is used only to make them connected, to tell them that there is some other node waiting for data, and there is this node which publishes the data. So comparing these three types of communications we discussed, topics, services, and actions, there is a table featuring differences between them. So topics are asynchronous. We know that data is just streamed into the topic, and anybody can just connect and read. So it's asynchronous and unidirectional, because we only stream data one way. And it is used for continuous data transmissions. Imagine you want to, for example, today we will have an example where we will stream sine signal, and topic is a good choice because we want to continuously stream data. We should choose topic. So then there are services which are synchronous because they're blocking. We wait for the response, so they are synchronous. And bidirectional, because we send the request and get the response. So data is traveling both ways. Within the request, we can send some data, and within the response, we also can get some data from the server. They are used for request-response communication with fast request processing. And actions are asynchronous and bidirectional, so they're featuring properties of previous two. They're asynchronous as topics because they're not blocking, but they're bidirectional because we also send requests and get feedback, and then in the end get some response. And they used when service mechanism is not applicable due to the long request processing time, or when feedback is needed during the request processing. For example, we want to know what is the state of our task, how far we are from completing our task. In this case, actions are perfect. And the last theoretical thing we will discuss today before switching to creating package again and to creating our own nodes are messages. So Ros uses simple message description language. Last time we discussed with you shortly standard types of messages which are there in Ros. We will take a look at them in a couple of minutes. So, but there is a specific language you can use in Ros to describe new types of messages. And actually all even standard types of messages are described with this language to be easy to understand. And this message description language is then translated into code automatically with Ros. So this is something Ros performs for us. It generates message description from message description language in several target languages. By the default, Ros generates it in Python, C++, and Lisp, because these are three the most common languages for Ros, but there are others, and you can generate for other languages. So basically what happens, Ros takes our short message description written in specific language for Ros and generates programming files, for example, models if we talk on Python, or header files if we talk on C++, just automatically. There is actually huge files with classes, enums, and so on, just generated for us by Katkin and by Ros. This is really convenient. So we don't have to write new programming files, source code files. We can just write short description and everything will be generated for us. Custom message types are described in files with MSG definition, and usually we store them in MSG directory within our package. So if we want to add our custom message, and we will do that today, I hope, we just create a directory within our package and put specific files with messages description into this directory. And messages can contain two parts. First of all, there are data fields. So these are fields which contain some data in our message. And they have a description in the format type and name, the same as in any programming language with a strong typization as C++. And also we can define constants. These are just for interpreting data fields. For example, if we have data field with integer from 1 to 10, we can create constants which will interpret our integers in some particular way, just for our convenience. For example, 1 can be debug, 2 can be warning, 3 can be error, and so on. So this is just for convenience. We can create constants which are quite the same like enums in C++, if you're familiar with them. So let's take a look. This is an example of a sensor message. This is a standard package defining messages for different types of sensors. And here we have example for IMU. Let's actually take a look. Sensors, messages, Ros. So this is a standard package coming with Ros. And it defines different message types for different types of sensor. You can see some joystick, laser scans for lidars, magnetic field for magnetometers, point clouds, again for lidars or stereo cameras, temperature for temperature sensor, image for camera, and many more. So all these data types are already defined and created for us, and I recommend you working with Ros. First, take a look on which message types are already there, and like 99% of time you will find something which suits you already, and I recommend you to use standard ones as much as possible, because for them there are many debugging tools, visualization tools which are already in ROS. If you create some custom data type, you will be able to visualize it with different ROS tools, but sometimes some visualizations can be unavailable, and that is why it's better to use standard message types if you can. And for example, there is IMU sensor message IMU message type, and you can see the whole description here. There are some comments what this message holds, which are measurement units and so on, and we can see from which types it consists. Let's get back into the lecture. There is the same example. So it consists from header, and header is a specific message type which we will use a lot, and we will discuss it a bit later today. So as you can see, these data fields can contain like just simple data types and also arrays of static and dynamic lengths. But they also can contain already existent messages. So for example, sensor messages IMU, one of the fields contains another message, which is geometry messages quaternion, which is simple type of geometry messages used to express orientation. So we can combine different message types, even defined by us, within a new message definition. And this is really convenient. For example, here for linear acceleration, we also use vector3, which is geometry from package geometry messages, also standard type of message. And we're combining all these data types, we get a new sensor message IMU message type. This is really convenient. So we can take our own messages and combine them to get a new message type, which will be distributed within the topic. And regarding constants, we can define different constants. For example, x is equal to 123, and this would be convenient because we can access it by just typing message.x, and we will know that there is some constant hiding behind this. This is just for convenient. We can define constants also in our messages definition. So that's it basically for theoretical part today. Let's try to work with all this and on practice see how all this works. So first of all, we will go to our Docker container. Just let me, if you're working within Ubuntu, of course, you don't have to, and you have your ROS installed, you don't have to run Docker container. If you're working with Docker as me, let's remind ourselves what this command does. This one allows us to launch this, actually the whole one till here, allow us to launch Docker with graphical interface. So we will be able to launch graphical applications from within the Docker. And this is convenient when working with ROS, because ROS comes with many debugging and development tools which have graphical interfaces. Last time we launched Turtle Sim, for example, this simulation, and without this command, we wouldn't be able to have these graphical interfaces. This command just means to clear Docker after we stop the containers. This is also just for convenience, because if we just stop the container, it can remain in memory, and we will need to perform some specific operations to clear Docker memory. This is us giving a specific name, and it will allow us to launch new terminals from this Docker with this simple command, accessing it by ROS name which we gave here, because otherwise we would have to search through all running containers, see the ugly long name from letters and numbers, and put it here. If we give a specific name to our container while launching it, we can just put this name here to launch new terminal. And then we are specifying which container we are running. In my case, I called it ROS full. You could give a different name while building your Docker image. If you gave different name, you should use some different name here. But I think I hope you gave this standard name for convenience, just to repeat after me. So let's launch our container. We've got inside. Let's see what we have here. You should have these two files, which were in the archive next to Docker file itself. We will use these files in today's lecture to program our first two ROS nodes. But for today, for the beginning, we have to create a package. So there is a slide. You could copy comments from the slide for convenience. We performed it last time, but we didn't save changes, so it's better to start from the beginning today. So we're creating our workspace, and we call it my Ros workspace, and we're creating src directory, which is a necessary directory within which we will create our packages. So this -p allow us to create all the directories on our way, even though none of them were created. So let's start from it, copy it, and we should have now, if we go to our home directory where we created our workspace, we should have our workspace. That's correct. And then switching to this workspace, we should have our src directory here. So everything worked fine. I'm using Control L sometimes just to clear the terminal, just for convenience. So Control L allows you, it actually puts many empty lines into terminal. And this is just convenient if you have many commands already typed here. You just click Control L and it gets clear. So now let's initialize our workspace. As you remember, with command cat-make, we both build our packages. And if we don't have any packages, it will just initialize our workspace. And by initializing, we mean that it will put specific file to mark that this is a Catkin workspace. And also it will create directories devel and build, in which it will put our packages when we will have some. So it will compile them and put into these directories. But since we don't have anything here yet, we should call cat-make. But if we just try to call it, oh, it will work, because in Docker file, I included specific command to source for us. If you remember, starting working with Ros, we should have first actually source. In this case, in this case, you should use zch, because you have zch inside your container. If you're working with bash within your system, you should use bash instead of zch here. So if you remember, we first should have to source Ros in order to make all Ros infrastructure available. But since I prepared the Docker image in such a way that this command runs automatically each time we launch our Docker image, so in this case, cat-make is available already without even sourcing. But if you work on your own PC, you should first source setup zch or setup bash. So cat-make, and we see that no packages were built. There is no information about some packages being built, but everything runs successfully. And now we have built and devel directory, and actually our workspace is initialized. Yeah, and if you list all files, even hidden files in the directory, let's make it again, ls -l -lla, you can see that there is actually hidden file. Files starting from dot are considered hidden in Linux, which is just some file indicating that this directory, my Ros workspace, is a directory which is Catkin workspace. So actually, Ros search for such files to know that this is a workspace. So this is just an empty file to mark that this particular directory within our Linux system is a Ros workspace. And this file also was created by this command, cat-make. Okay, now let's move further and let's create our first package. We have to change the directory to src because all packages are stored within our workspace src directory. Now we're here, root my Ros workspace src. If you're trying to repeat after me and I'm going too fast, just type into the chat. I will try to slow down and explain something again. So just let me know if you're trying to repeat after me. So we're in SRC directory. Now let's initialize our package. Last time we discussed that there is a specific command called catkin create package. Then we specify package name, and then we give it some dependencies which we know our package will depend from. Actually, we can ask for some help and see what are the options here, and we will see that there are actually many options this tool can perform. So for example, we can specify system dependencies, we can create meta packages, which is this command. We can add some description right away, so it will put this description in package.xml right away. We can specify author, maintainer, and many things. We can do it afterwards just by modifying package.xml file, because we know that this command just creates a package.xml and CMake file for us, in which it already includes these dependencies we specified. We can do it all manually afterwards, and actually advanced Ros developers do it manually usually. But for now, it's really simple for us to ask this command to do everything instead of us. So we create package. It reports that it created CMakeList, package.xml. It also created test package SRC directory or folder for us, because we called our package test package, and there is a SRC directory in which we will store our files, our source code. And it also suggests that we have to tweak package.xml in order to specify some information we want to specify, as we said, maintainer, package description, and so on. So, okay, now let's do the following. Let's switch to our test package. So we're inside our test package, and let's open some Visual Studio Code Reductor or IDE, which I also installed in your image, in your Docker image. So this command just launches Visual Studio Code, but since we're trying to launch it from within the container, it also asks for some specific argument. This is the directory in which it will store some log files. We can specify directory, but actually we can just leave it empty and it still will work. So, okay, we'll open Visual Studio Code. Let me try to make it a bit bigger. And here we see that we are within test package directory, and we have a SRC directory which is empty, and we have two files, CMakeList and package.xml. So the same as in terminal, but in more convenient way. Let's open CMakeList, and there is one thing I would suggest you to do. As you can see, this file is just white. Everything is in white. We don't have syntax highlighting here, but we can install some extension for working with CMake, and it will make our life much easier. I think it should be the second one. Yeah, let's install. There are many of them. We will install the second one, and now if we open our file, you can see that now syntax is highlighted, and it's much easier to work with it. For example, commented sections are in green, functions of CMake are in blue, and other texting is in white. So this is much more convenient. And this is the same CMake list we discussed. So this was generated automatically, and this is really good because it has all comments helping us to configure this CMake list if we change something. And while we're developing with Ros, we will have to uncommit or modify one or another section. And it has a lot of description of how to modify these sections in order to make it work. But in the most simple case, it already has all commands we need. And let's remind ourselves what this command do. And actually, we even have help here on specific CMake commands. And this is really convenient. to work in such IDE as Visual Studio Code because it has a lot of information for us. So first of all, we define minimum version of CMake. This is actually not necessary, but a good practice working with CMake. Then we define our project, and in this case, our project called in the same way as our package. Then we find packages, and if you remember, we said that our package will depend on two packages with this command. While creating package, with kite can create package, we specified that our package will depend on two other packages, Ros Python, which is client library to work with Ros from Python, and standard messages, which contains standard message definitions such as float, boolean, and so on. So, and Ros already says that we have to find these packages because we depend on them. And then the simplest command Catkin package just prepare all needed information to create package and include directories needed because we depend from these packages. It just includes directories in which these packages are defined. So, and that's it. That's the simplest way to build our package. If we will add something more complex, we will modify this file. And today we will generate our messages. And you see that there is the whole section on how to declare Ros messages, services, and actions. They all declared in the similar way. And there is whole description how to do it in proper way. So we will need to uncomment this part, but we will return to it a bit later. And let's take a look on package.xml. You can see that there is also syntax highlighting, which is here by default because this is a standard XML format. So we can see that there is version of XML format. There is name specific tag, which specifies name of our package, version, description, which was generated automatically. And you remember that in this command, we could specify description if we run ---- help. We could specify description -d flag and give some text description, and it would be here if we gave it. There is maintainer, and there are also important part on dependencies. And we can see that we depend on build stage and on execution stage. Both we depend from Ros Python and standard messages as we specified while creating our package. So the next step for us is to try to work with all these types of communications we discussed. So we discussed that there are topics, services, actions. So with services and actions, we will work on the next lecture. Today, we will create topic first with a standard message type, and then we will try to define our own message type, like here, and change our standard message type to our new custom message type. So for that, we will use files which are already inside our container. Let's change directory to src within our package. And then you remember that in root directory, there are two files which are signal filter node and signal generator node. These files are prepared in advance. Let's copy them to our src directory. For that, we will use command cp, which stands for copy. And then we will specify this file, and we will say that we want to put it into the current directory. Let's see if it's here. Yes, so we copied the first one, and let's, in the same simple way, copy the second one. So the second one from here to our current directory, which is specified by dot, because we are already in the directory we want to copy file to. Okay, let's make sure that both files are here. We will see what is inside these files a bit later, but first let's try to build our package now, because it already has some code. Let's go to the test package and run CMake, I'm sorry, not CMake, Catkin make command. So this is the same command we used to initialize our package. And now we will use it to build actually our package because it already has some code inside. And we didn't even need to modify CMakeList. Let's try to build it. A package, but Oh, I'm sorry. We are in test package directory, but in order to build everything, we need to go back to workspace directory. So now we're in workspace, and from here we need to run cat-can-make command because it builds all packages within our workspace, and we need to run it from this directory. And you see we got some error. It says that in test package CMakeLists.txt, line 53, there is some bracket. I think while showing you I broke something. Let's see. Yeah, you remember I was uncommenting these lines with message generation, and I accidentally didn't comment one bracket back. So let's fix it, and let's try to build it again. Okay, and now there is something different. You remember last time we had really short output of this command because we didn't have any package inside our workspace. Now we have package, and Katkin says that it tries to build some package, which is called test package. It's processing it, and we can see that everything went correctly, actually. So, okay, now we have our package built. We need now to source from the devil directory. If you remember, there is a devil directory we worked last time. And in order to add our packages from our workspace to Ros, we need to perform source after each time we run this cat-can-make command. So each time we build new packages or build new version of our package, we have to run this source command again in order to make Ros know that there is workspace in which there are new packages which we created. So we source first, and then after which there is a simple way to check if Ros knows about our package. You remember that there is Ros Run command, which runs some packages from Ros. For example, last time we used it to run turtle sim. You remember? So there is a turtle sim package, and we run some nodes which are within this package. And if we made everything correctly, Ros Run command should now know about our package, which we call test package. So let's try. If we type test package and double tab, we see that Ros Run already knows about our package. That's great. That means we made everything correctly. But if we try to tab here, it doesn't suggest any nodes from here. So for example, with turtle sim, if we double tap here, it knows that there are 4 different nodes we can launch from this package. In our case, it doesn't suggest anything. And there is a reason to make our scripts launchable. We have to make them a permission to launch. So in Linux, if you're familiar, everything is a file, and different files have different permissions. So to be written, to be readable, and to be executable. And this is exactly what we need to do. We need to give our files permission to be executable. It is performed with change mode command, which you need to run with sudo. Then we specify what we need to do, and in our case, we use +x, which means to make executable, and then we specify files which are from test package, from src, signal filter node, and then signal generator node. Okay, we made both files executable. We can actually check it with ls-la command to this folder, and we will see that they both have access here, which means that they can be executable, these 2 files. And you see that they're in green, which also signals that these files are executable, so they can be launched as a separate process within Linux. And now let's finally try to launch the first one. We will see what is inside in a minute, and we'll discuss how these files were written, and we will modify them. But first, let's try to launch. So from Ros Run test package, And you see now that Ros suggesting us these two files, and we will start from signal generator node. Actually, we will do a simple example within this and next lecture. We will have two nodes. One is called generator. It will generate some signal. In our case, it will be noisy sine signal. And the second one will be called filter, and this node will subscribe to this signal generated by the first one, and we will try to filter signals. So from noisy sine signal, we will try to get clear sine signal. We will do that with moving average filter. And today we are working just with topics. Next time we will try to add services here. We will change parameters and so on. So this is a simple example we will use to study basics of Ros. So let's launch signal generator, and we trying to launch it, we get an error. And this is right because if you remember, we have to first to run Ros core. We didn't run Ros core because that is why there is no Ros master, and Ros cannot work without this. So let's start from Ros core command, and ampersand stands for sending this process into background after launching. So we launched our Ros core, and now let's try to launch our node. Okay, we see that it is working, but nothing happens. We don't know what is inside, but we see that it launched, it didn't crash, it occupies our console, so we cannot do any new command in this console, but we don't know what is going on inside. Let's try to find out, and this is actually how you often debug your Ros. Let's launch new console within our container with command exec, name of our Ros, our Docker image, and command which we want to execute. And in our case, this is zch because we want a new terminal window. Then we remember that we need to source, but in this case, since sources happens automatically because we wrote our Docker file in this way, we don't have to source anything. We can directly start working with Ros. Let's try to see which topics are published in our system to see what this signal generator is doing. So Ros topic list, Ros. Oh, actually, it seems that source didn't happen, so we need to go to source manually. Let's do that. And now let's try Ros topic again. Okay, we see that there are 3 topics published in our system. We know that Ros out and Ros out aggregation are standard topics for logging. And there is something new, some signal topic. And we can check who publishes this topic. We do that by command Ros topic info, and then name of topic signal. And we see, let's do that just again to see clearly. We see that this topic has specific type, standard messages, float 32. And you remember that our package depends on standard messages. So everything is correct. And we see that publisher is some signal generator, which has some particular address. But for us, it's important that this is a signal generator. So this is the name of this node. And there is no subscriber because nobody reads this topic. And let's try to see what is inside this topic. For that, we can use command Ros topic echo. And then we will need to specify name of topic, and this is signal. And we will get data which is published in this topic. We see that there is some field data and it has some value. And I told you already that this is a sine signal, noisy sine signal. But this is not really clear from here which shape this signal has. You remember last time we used RQT graph, specific application for Ros, which shows us some Ros graph. We can take a look at this again. We see that there is a signal generator node. This ellipse stands for node. And if we remove dead things here, dead things are the topics which are published by somebody, but not read by anybody. If we remove this error and change from nodes only to nodes and topics, we don't see anything. That is weird. Oh, this is leaf topic. Sorry, not that thing, leaf topics. This is called leaf topics, topics which are published by somebody, but not read by any other node. we can see that there is signal generator node, which publishes signal topic. There are other tools from RQT. If you just launch RQT, you will get such a window in which you can find different debugging tools for ROS. Let's make always on top. There are different so this is the whole system for ROS to debug different things. It is extendable, so you can even write your own extensions, your own plugins to this thing. This is not only debugging tool, but this is the most simple one in ROS. So we will start from it. And there are different plugins. For example, somewhere this is our Ros Graph tool. Let's find it. Yeah, node graph. This is the extensions we used, so the same. So we can launch it from here from plugins, and this actually RQT graph command we used before. This is just a shortcut to launch this window with this plugin. But there are many more plugins. Let's close this one and see a plugin which is in visualization and called plot. This is the simplest plot builder in ROS. There are many more advanced ones which can build multi-plots, which allow you to perform some math with plots and so on. But this is the most simpler one, which allow us to build some plots of some signals. And let's try to specify in the field topic our signal topic and press enter. We will see that there is visualization of data we get in our topic. Let's try to tweak it a little bit. So you need to unpress after scroll, choose this tool here, and then with the right button, I think, with the left button, you can move it sideways. With the right button, I think you can scroll it, but for some reason, it doesn't work well for me. I actually have laptop, so it's not really convenient with touch bar. Just a second. I will try. Okay, you can scroll right. You can press right button and scroll right and left to change the scale. So on this scale, we can see that this is something resembling sinus, but with some noise. Let's press auto scroll again, and we will get data in real time. So this is the same data as we will get from the ROS topic echo. This is the same data, but visualized in plot, which is really convenient because we cannot just understand sinus with our eyes. It would be really impractical. So let's try to launch another terminal, to launch our Docker, to source, and to perform echo command. So this is the same data which is published here, just in the form of visualization. And this is really convenient. As we said, this is the most simple plot tool in ROS. There are much more advanced because you work with numerical data a lot when you're building robots. But for our purposes right now, it is really convenient. And we can see that this is from signal topic, from data field, because within our topic, there is data field in which we write this data. Okay, let's close it for now. We will return to it a bit later. And let's actually open our Visual Studio Code to see how this node, how this code which publishes this data is written. So let's use code with this flag user data dir. Oh, I'm sorry. This one. To open our Visual Studio Code, but this is a bad idea to open it from root. So let's go to our Ros Workspace, SRC, test package, and let's open it from here. Okay, so now what we have here in our test package, maybe there are some questions till this moment, or something is unclear, or I have to repeat something. Just text in the chat. Okay. If everything is clear, let's continue. So we have our test package. We have src directory to which we put our two nodes. We have CMakeList, package.xml. You know this already. So let's take a look at signal generator node. And this is actually how we write code for ROS in Python. So this is a simple example. This is not the simplest one, but it is quite close to the simplest one. Let's discover it step by step. First, we import ROS.py library, which we know the client library, which allows us to work with ROS from Python. Then there is a standard NumPy import. We will use it to generate our sine signal. And then from standard messages, we import float32, which is type of data we will stream in our topic. And we can take a look at standard messages once again. So there is a package called standard messages. There is a package description, overview, and we can see all different standard types which are defined in ROS. These are the most basic types. So usually more complex message definitions are built from these types. And we can see that there is float 64. This is the one we use, right? No, float 32. There is float 32 message among others. And if we open it, we will see that the message of this type contains only a single field called data and having type float 32. So this is the type of message we will use in our simple message generator node. And that is how we import it from standard messages package. So then we define a class called signal generator. This is not a necessary step. We could just put all next functions as a functions without placing them in the class, or we even could just place everything into our main function. But just for convenience, I decided to create class here, and I called it signal generator. So in a init function, what we do here is the first important ROS related thing. We define the first publisher. So from ROS.py, we define publisher, which is actually a class, and we save it into our variable called signal pub, which is a variable of the class. And in this publisher, we will publish to topic called signal. So that is where we define the signal name of the topic. And into this topic, we will publish data with the type float32. And there is a third parameter we defined here, which is queue size. So if we will publish too fast, there will be some queue of messages, which in our case will have size of 10. So if we publish too fast, there is a queue of 10 messages which can hold data and publish them. So this is quite an advanced concept. We don't need it actually at the moment. If you work with complex system where throughput and latency are important, you can change this number. For example, if you want to receive only the latest data without any latency, you have to put the minimum size of queue, which is 1. So no data is stacked into the queue. So there is no chance you will get some old data which was queued long time ago. You get only recent data, because once new data is coming, it just substitutes all data in the queue. But this is for more advanced systems. So actually what I wanted to add here is that in the end of this 9th lecture, you have some slides describing the same what we described now. So how to work with Ros.py API. And there are many more parameters described here. You can see that, for example, in case of subscriber, there are many more parameters. And in case of publisher, there are also many more parameters. So there is a more rigorous description on the slides. You can check them, these 2 slides after the lecture to see more. And also there is a link to Ros.py API, which you can read. There are many, many more things that we are discussing, more advanced parameters and many more, because this is a really adjustable system. But for simple example, we don't need all that. We just need to know that the first parameter specifies the name of topic we will publish. And we saw that the name of topic really was signal. So when we were reading the topic, this is the name we were using, and it publishes data in format float32. Then we will go to the function called launch signal generator. This is the function which is called from the main. So in main we first create signal generator, so this class, and then we call the method of signal generator class, which is launch signal generator. This is just an arbitrary name I chose, and what's important here is that inside this function we call it just once, and inside this function we initialize our node, so rospy init node. And here we give a name to our node. And also remember when we were working with it, seeing which node publishes signal topic, we saw that the name is signal generator. And this is where we give this name. Actually, it doesn't matter how our Python file is named. We can specify any name we want here, and it will. This is how we will see this node within our Ros Graph and within our system. And then the last part here, we create a specific variable called rate, again with rospy rate function. This is a really convenient way to publish data with some specific rate. What it does, it specifies rate we want. In our case, we put 10 Hertz here. And then we will call within our cycle, which is infinite cycle. Actually, it is not infinite, but it works until ROS is shut down. And there is a specific function, rospy is shut down, which checks if ROS master is still working. And once it's shut down, this cycle also will shut down. Really convenient. So once you kill master, you kill the whole ROS system if it's written in this way. And here is the rate sleep function. What it does, depending on how long previous commands within this cycle took, it will adjust the time it sleeps to stay within 10 Hertz. For example, if this command works really slow, this sleep will be tiny to try to work with 10 Hertz frequency. If this part would be really fast, this sleep will be bigger in order to provide 10 Hertz we asked. And this is adjusted dynamically. So this command can take different time on different launches, depending if there is something happens, some processing of data. So this sleep will be automatically adjusted, and ROS will do its best to try to make this cycle work with 10 Hertz frequency. And this is really important in robotics because sometimes you really need some specific frequency of specific parts of the system. For example, you want your localization to work 100 times per second because you need it in your path planning with this particular frequency. Or especially working with sensors. If you are, for example, odometry works slow, you don't get enough data to estimate your speed. So your frequency of your odometry should be quite high, and this is how you can try to perform with high frequency and be sure that this frequency at least will be like ROS will make its best effort to keep this frequency. And there is one command, this one we didn't discuss, which works in the cycle. This is also the function I wrote. And this function does the following. First, it gets current time. And depending on this current time, it generates new signal value, which is sinus from this current time. So we need sinus from time to generate real-time sine signal. And also there is some random noise multiplied by some constant in order to perform noisy signal. So if we comment this part, we would get just pure sine signal, which depends on time. And here we add some noise because then we want to filter this noise. This is the example how we use two nodes. One generates some data. We can imagine that this is some noisy sensor, and another one filters this data. And then we publish with a specific method of our publisher. So you see publisher here, that is where we created our publisher and stored it in self-signal_pub variable. Here we call the method of our publisher, which is publish, and give it the data. And since this data is float, and we used this data when we specified our publisher, we can just pass this data here as an argument of this method of our publisher. And that's it. So once again, we create our class, signal generator class. Within this class, we call the method which initializes our node with a specific name, and then just works infinitely until ROS is working. Once ROS is shut down, this cycle also will shut down. And within this cycle, we each time call the method which generates new sinus value and publishes to the specified topic. And then we just sleep until 10 hertz time is passed. So we try to publish this data with 10 hertz, so 10 times in a second. So this is the simplest node. Let's try to run it once again and perform. Oh, actually, it's still running. Let's see that it is still running by command Ros topic echo signal. And once again, this signal is coming from here. That is where we define our publisher, and we say that it should publish to signal topic this type of message. So let's see if it still publishes. Yes, we still see it. And now let's actually, and there is warning because we had some connection. This is just a standard warning Ros gives us that there was some connection to topics this node publishes, and then this connection disappeared. You see TCP/IP connection failed. So we stopped our echo, and actually echo just subscribes to topic to present data into console. And this is just a warning from Ros that there was a subscriber, but there is no anymore. There is specific Ros topic command which called HZ to see with which frequency we publish this data. It subscribes also to this topic, and you can see that average rate is 10. So we asked Ros with this rate and with this sleep command to publish 10 times in a second, and we can see that it handles it successfully. There can be deviations sometimes because Ros is not real-time system, and it is not guaranteed that it will publish with exact frequency, but at least it tries. And for example, if you launch a complex system, these rates can fluctuate a bit because complex system computes, consumes many resources, and then Ros becomes unable to publish with the rate we asked. But since we have a really simplistic system, it successfully publishes with average rate 10 hertz. Okay, now there is one thing which is also not really convenient about our node, which I personally don't like. You see that there is no some output. So when we run Ros Run test package signal generator, there is no output, and we basically don't know if everything goes correct or everything goes wrong. So let's try to add some logging to our system. For that, on the slides, you also have this explanation. There is a standard way of logging things in Ros. There are different levels of log. For example, we just saw this warning. This is a warning type of log. There are different ones such as debug, warning, error, fatal, and log info. There is a really convenient system of working with logs in Ros. You can specify different levels. Then you can filter out with specific graphical tools. You can filter out different levels of errors, and you can see either there were errors, warnings, or there is some just debugging information which you want to have when you debug your system, and then you can switch it off while you launch your system because there can be heavy debug outputs. And you don't have to modify your source code. So in your source code, you can just specify in different places, you can specify different outputs like this, and then you can switch them off without changing your code. Ros will know that you don't have to publish some particular levels, for example, debug and info, and only publish warning and error in real working system. So for now, we will use simple info level, and we will place it here, and we will specify that our node will text signal value, and then it will place to these brackets with this format command signal.data, but actually in our case it's not signal, it's new signal value, and we don't need data field. So just new signal value, we generate new signal value, and then with log info publish it to log console. And let's add another one after initialization, because we want to know that everything went correct and our node was initialized. Let's place another one here, and let's, without format, just text value, let's put here, I am initialized. I am initialized. Okay, so we don't have to recompile anything because we work with Python. So we can try to run signal generator once again, and we will see that there is first message, I am initialized. There is a specific format of logs our Ros uses. We can see that there is, first of all, level of logging, and there is info. There is timestamp, which is also really important to understand when this log was acquired. And then there are signal values. We can see that we put it here. Different new signal values are also streamed right to the console. And now at least we understand that this node is launched and works correctly. But there is more. You remember that there is a specific we discussed it in the very first Ros lecture. There is a specific debug node which called Ros out, which is launched every time Ros master is launched. And this Ros out collects all Ros out topics. And to Ros out topics, these are exactly these prints are also going not only to console, but also to this Ros out topic. And this node Ros out collects them and do two things. First of all, it publishes it to Ros out aggregation topic, and we actually can try to see it. Ros topic echo Ros out agg. And there is empty. This is interesting. And what if we do? Okay, let's. That is weird. And also, but let's move further. And also, it writes this data into the log files. You remember that Ros has some specific log files which are in our home directory .ros logs. And for convenience, there is latest, which is logs for latest from latest launch. We can see that there are some logs, and for some reason there is no log for our node. This is quite weird. I don't know what's went wrong. Usually there is. Okay, I will check after the lecture and I will let you know why there is no logs for our node. This is weird. But for some reason there are none. But usually with this info, there should be additional log file named after our node name, and there would be the same logs as we see here with these commands log info and log warn. Let's actually try to change it to log warn and log once again. Maybe there is some configuration of Ros, and for some reason log info is now is switched off, so it doesn't log it. You see, if we change it to warn, there's different color and warn level here. And let's see once again. No, for some reason there is nothing. This is quite weird. And even in Ros topic, Ros out egg, there is nothing. Okay, I will check after the lecture what is the reason for it. But now at least we know how to use logging within Ros, and we can add simple logs here, which are convenient to debug and to see what happens inside our logs. And let's see the second file, which is our filter node. We didn't try to launch it yet, and we will first discuss what is inside, and then we will try to launch it. So our signal filter node is quite similar. It also uses ROSPy, of course. It also uses the standard message float 32. It also defines some class. In this time, it is called signal filter. In initialization, it is a bit more complex because last time we only had publisher, so we only publishes data in signal generator, so there is a single publisher. In our filter node, there is already subscriber and publisher, so we will subscribe to signal topic, and we know which data will be streamed in this topic. and we will publish filtered signals. So there will be input to our node and output from our node, which will output filtered signal. We also defined some variable called signal window, which is queue of size 5. So there is a limited size of our queue, and once new data is coming to queue, the oldest data will be dropped out. And the size of the window will be 5, and at least now. Next lecture, we will try to parameterize it with Ros parameter and see how to work with Ros parameters, so we don't have to change source code every time we want to change window size. So, and what we do here, important part is subscriber, because subscriber have a bit different parameters from publisher. It also says to which topic it subscribes, which data will be streamed into this topic, but the third argument is callback. So the callback is a function which will be called every time data is coming to this topic. So we subscribe to the topic, and each time we get new data from this topic, we call some callback. And we do whatever we want within this callback. So here we define this callback. We can define any function. We can use any function as callback. We know that there is signal coming, so this is just a name of variable, and this variable will contain whatever data is coming. In our case, we know that this float 32, but there could be image, anything. So we know that second argument in callback will be the data which is published into the topic. And then what we do in this particular callback, we first generate log message that we've got some new data, and we know that within signal there will be field data in which data will be streamed. You remember we have seen that in float 32 there is field called data, and that is where a numerical value is stored. And then we will try to filter the signal, and for that we will append new signal data to our window, which is size of 5. So there will be always 5 last signals in our signal window. And then we just compute average. So we sum all data in this window and divide to the length of the window, which is 5. And we will get average of last 5 signals. And we will publish this average to filtered signal topics. So there is a publisher we created. Again, from this publisher, we call a method called publish, and publish filtered signal to there. There is one interesting thing, one difference between generator and filter. You remember here to run the thing, we used this while until RosPy is shut down, and everything was working within the cycle, infinite cycle, which works until Ros is shut down. Here we use different technique. Since all the processing is in callback, and we know that callback anyway will be called every time signal is coming. So every time data is coming to topic, our callback will be generated. We use a different callback, a different approach here in main. We first of all initialize node here and give it a name signal filter. Then we create new signal filter, this one to create subscriber and publisher. And then we perform command which called RosPy spin. And this command just gives the whole control of our node to Ros. So basically we give the control to Ros and do not do anything anymore here. And what happens here, Ros knows that there is some new data coming to this topic. And every time data is coming, callback is called. And all of what we need is running within the callback. So we don't need to perform some additional operations here. That is why we're just returning the control of our node to Ros. And that is how it works. So if you have logic that everything within your node happens only when data is coming, you can use the same technique, only callbacks, and you give the control to Ros. If you know that you, between callbacks, for example, or between publishings, you will need to perform some additional operations, you better use this structure, because in this while cycle, you can put many more different functions as any function you want, basically. So there are two different ways to structure your nodes, both working. You choose one depending on which type of node you are writing. So if you don't have questions on this code, let's try to see how filter and generator work with each other. And I think that it will be it for today's lecture. So next lecture, we will define our own type of message, and we'll try to work with services, with Ros parameters. So do you have questions on this code for now?
I have a question. What if, like, we want to simultaneously have a callback and also publish some data in a while loop? Just like you said, if I just write while and my code will it be able to perform callbacks? Like it should do it somehow asynchronously, I guess, because well,
Yeah, this
if
is
you're
a
just
really good question. I think I understood it. Let me see if there is, I think in the next lecture there will be a specific slide about it. But for now, there is a really simple technique. So there is ROSPy spin function, right? This used to give control completely to Ros. But there is another function. For example, imagine we have this cycle here, and also we would have a subscriber here. So we both have callback, but we want this cycle to perform some actions between callbacks, right? What we would do
yes.
here, we would put function which is quite similar to ROSPy spin, but is called ROSPy spin once. And what it does, it checks for callbacks, perform callbacks if there are some new data, and then returns to this while cycle. So we would do some new signal generation here, some new methods we would like here, and then again check if there is new data, run all callbacks, and so on. So that is how we would go if we would need to combine both approaches.
Okay, I see. Thank you.
Yeah, this is actually the third way we didn't discuss today, but this is an important one, yes, because actually majority of times you have nodes which both publish, do some processing, subscribe to some data. That's right. We have really simple nodes today, but usually things are much more complex. So that was a really good question. So, okay, let's finally try to run both. So we first run our signal generator node, and since we added some logging here, we see some data. Now let's try to Ros Run test package. Okay, we didn't source here, didn't source our particular workspace. You remember that after compiling, we need to source from devel. So set up zsh. This is why my Ros didn't know about test package. So now it should work. Yes, it works. Ros Run test package signal filter node. It also has some logging. So this one says signal value, and this one says I've got something. And now let's try to build plots of both. We go to RQT tool. We already have, so it remembers last launch. So we already have signal here. We can see that there is signal data. And now let's first start from seeing our RQT Ros graph. So let's start from, actually you can see that we can have both within some window. So this is really convenient tool. So now we see that there are two nodes. One is called signal generator, one is called signal filter. There is signal topic between them. And if we again remove that things and leave topics and we will choose nodes and topics, we can see that signal filter reads signal topic and publishes filtered signal topic. Let's now close it. I hope it was seeable for you. Let's close it and let's add here filtered signal, right? It actually also helps. Let's add filtered signal. It automatically adds data. And now we can see that there is some filtered, which is in red. Border spacing. Okay, there somewhere here should be a way to make them a bit nicer, but okay, here curves. Let's make one a bit thicker, yes, like this. So we can see now that we've got something really smoother than before. So we really filtered our signal. The red one, which is signal, filtered signal, is already looks much more like sine, but still has some noise. We also see that there is some lag, some delay between the initial one and filtered one, and this is a property of average, of moving average. It introduces some delay, and the bigger the window we are using to filter signal is, the bigger delay is. So with windows like 15, we would get even bigger delay. So there is always trade-off on smoothing data and getting a delay. But in our case, it works. Data is much more smooth. And now we have a system where one node is publishing data and another node is reading this data and filtering it. And this is much like a real system in robotics. There are a lot of such communication where some sensor publishes some data, and then we have the whole pipeline of nodes performing some computations with this data, filtering them, detecting something in them, and so on. So this simplistic system we have built today is really close to real nodes we are using, with some exception that real nodes can have more complex logic and a lot more subscribers and publishers, because sometimes we have to get data from several sources to do something with them, and so on. So we will continue working with the same code on the next lecture. We will modify it. We will first introduce our own message type, and we will substitute this simple float32 message we used today to some specific, some custom data type, message type we would program next time. Also, we will discover new types of communication, which are services and actions. And we will work with parameter server, as I said, to control this window length we use to filter our data, not compiling or not modifying source code anytime, but just changing the parameter value on Ros server parameter. So that's it for today. Again, you have some notes in lecture slides you can get familiar with to see more on how these definitions of publisher and subscribers and initializing of node works. The last important thing here, since we are going to continue working with the same container, you should save the progress we have in this container. I will anyway distribute my container, so if you lost your changes, if you try to repeat after me and you will lost your changes, don't worry, I will send mine modified container. But in order to save your progress, you can perform this. There are several ways actually, but the simplest one is to commit changes in your container. And you can do this with this command, where as container ID, you can use ID you used while building Ros image. In my case, this is Ros full. So let's try to commit. Here I will use, actually I need to run this command outside of, no, inside of Docker. So we use Ros, and here, for example, this is a good practice to put surname and name. Oh, I'm sorry, I should run it outside of a Docker container, of course, but Docker container should stay running at the moment. That's it. So we have a commit, and next time we will run this container, everything will be saved inside the container. If you're working with Ubuntu on your laptop and you're just pure Ros installation, of course, you don't have to commit anything. You just have files on your system stored, so don't worry. Anyway, I will distribute this container with changes we made today till the next lecture, so you will be able to continue from where we stopped. And next time, as I said, we will work with different types of communication and with defining our own custom message types. So that's it for today. All homeworks I received so far, I will give you marks and comments today or tomorrow, as I said in the beginning of the lecture. So do you have any questions so far? Okay,